All right, legends, it's wonderful to be working with you again, coming to you through the digital space. Welcome to the video notes today, and today we're going to be talking about our intro to confidence intervals. So welcome to intro to confidence intervals. So as we're going to see moving forward, we will do confidence intervals for proportions and for means. But specifically right now, we're going to be looking at confidence intervals using z-scores, as we'll see, and z-related, I should say, test intervals. And we call that z-score a critical value, but all of this is to come. What I want you to do is go ahead and pull up the 6.1 PowerPoint notes and slides alongside this video so you can have them for your reference. And we're going to go to slide 4. And the first thing you're going to notice is that I give you a proportion for an approval rating. This is for Joe Biden, okay? So the examples that I use in this video for the most part are going to be for proportions because your 6.2 video notes handle proportion calculations for confidence intervals. So it'll be an easy segue in to start looking at some proportions and see how they roll. Now, as you well know, and as I impressed upon you in class, confidence intervals are incredible things. They are the first time that we are going from our sample statistic, in this case p hat, and we are extrapolating outward like a bat signal into the universe of what the true population proportion might be. And we call this inference, right? And this is the first time in class that we are making an inference without any information about the true proportion P. Or in the case of means, which we'll do in a class period or two from now, we do it without any knowledge of the true population mean. All we have to work with is a single sample. And using that single sample, as you'll soon see, we can do many incredible things. So let's work with our approval rating for Joe Biden, which is 39% or 0.39. Now, I want you to move to slide 5. But before you do, I want you to note at the bottom of slide 4, it says that we gathered our sample. Our sample is size n equals 1,004 adults. Our p hat is 0.39 because that was the percentage approval rating. And we also have here a margin of error of plus or minus 4%. Okay, which in the case of, we translated 39% into a decimal here. So plus or minus 4% is plus or minus 0.04. Okay. So the first thing to keep in mind is that a margin of error creates your confidence interval. When you make a confidence interval, it is, in this case, p hat plus or minus your margin of error, which I'm going to write as ME here, which means to get our first confidence interval, we're just going to take 0.39, and we're both going to add and subtract 0.04 from it. So our first confidence interval ever, and this is when we're given a margin of error and given a sample statistic, is going to just be 0.35, because that is 0.39 minus 0.04, and 0.43. And we're just rocking and rolling there, right? We've got an interval. And what this interval represents is, and I want you to know it in these terms, right? A series of not only possible, but plausible values for the true parameter of the population, right? In this case, P, right? It would be the mean symbol if we were looking at the mean, right? So, and this should make good sense because in reality, right, finding a single value and being like, 39% approval. I did a sample. How confident am I in 39%? Well, probably not very confident because it's a single value. And as with anything, we do what's called the over-under, right? The phrase that I want you to have in mind when you think of margin of error is give or take. I remember growing up, this was a quote I would hear all the time from friends, from my parents a lot, often from grandparents too. They'd be like, it'll take an hour, give or take. And when they say give or take, they should give a number after that, right? It'll take an hour, give or take a half hour, right? So it's anywhere from a half hour to an hour and a half is what you're saying to me, right? So what we're looking at here is a series of specifically, I should say, plausible values. Values that are not only possible, but likely to be the true parameter P. Okay, so we have an idea of what this means. And as we'll see in future lessons, we're going to learn how to calculate these margin of errors and these confidence intervals in more complicated ways. Now, if you move on to slide 5, I want you to know it says all of the things that I've kind of gone over before, but some things to keep in mind. One, your sample proportion, p hat. That's what that's called, a sample proportion. You should be like, Mr. Mays, of course I knew that. What do you take me for, a fool? No, I think you're brilliant. But I want you to know that's another term for what's called a point estimate. Okay? So the point estimate, same thing as a sample proportion. These are interchangeable terms. I just want you to know that because I don't want you to see point estimate and go, what the hell is a point estimate? It's there. There you go. It's same thing as a sample proportion, right? Now we are using our point estimate to make decisions about the parameter, right? As it says there, the true population proportion for approval rating for Joe Biden in this case. And I want you to notice that the difference we observe in the poll versus the parameter is called the sampling error, right? And we should know that from sampling distributions. When you made a theoretical sampling distribution, last unit, we made a bunch of different ideas where we said, well, what if I took the same sample many, many, many times and used randomization? There'd be some variability in the different sample statistics I get, right? So for this particular sample, I got 0.39. But it could just as easily in a sample where I follow all the same rules and even have the same sample size of size n equals 1004. I could have gotten, 0.35. I could have gotten even lower. I could have gotten 0.29. I could have gotten any conceivable percentage approval rating, right? And we call that standard error or sampling error in this case. We say it's sampling error. And sampling error is just the amount of distance that you find between any given sample and the true proportion, or the true mean if we're talking about quantitative data. Okay? And we are using this to find a plausible range of values. That's what I say at the bottom of slide 5. So let's roll over forward to slide 6. Hopefully that's all sitting well with my legends at home. Okay, this is a reveal. You might remember this from class, where I tell you this sampling distribution that I've just talked about, right, that we also spent last units doing. Sampling distributions are kind of theoretical ideas. We don't really do them, okay? They are a theory. They are a concept that we use to understand how sure we are in our results, and to what degree we can trust those results, okay? Because the reality is I'm not going to rerun samples of size 1004 over and over and over and over again. That would be so much work. And a good sample of 1004 people is a solid metric to work with, as we'll soon see, to gain a sense of confidence in our data. Please excuse my nose. In reality, what the idea of a sampling distribution does is it helps us craft this margin of error. And we're going to use it to create a sense of confidence, and it will help us set our confidence level. So the big ones that we'll notice, and this will show up in future slides, but 80% to a lesser degree, but more often 90%, 95%, and 99%, with 95% being the most common, are the different confidence levels we normally set, and we call that a confidence level, when we are doing a confidence interval. So when I give you this confidence interval of 35 to, oh, that's not a confidence interval. What am I doing? Those were just various values that a particular sample might have had in this distribution. These were my confidence levels, or my confidence interval, I should say, from 35 to 43, 0.35 to 0.43, okay? I would say I am a certain percent confident in those values, right? And for my poll, it looks like if I go to that slide, I didn't tell you the confidence level of that interval. So, but let's say that that confidence level was 95% confident. What that would mean is, oh, I am confident, 95% confident, right? That's my degree of confidence. That's why we call it a confidence level. That the true population proportion lies between 0.35 and 0.43. And we'll talk in a slide or two about what that kind of confidence truly means, but just have it in the back of your head. Now, when we set the confidence level, what you're going to see, and actually I'm going to use the equation to really denote this. The equation for finding a confidence interval for a proportion specifically, you might remember from class, looks like this. P hat, so our sample statistic, plus or minus our margin of error. How do we get our margin of error, you might ask? Well, the calculation for margin of error is we have to set a particular z-score. We're going to touch on that in a moment, how we find that z-score. But that z-score is directly connected to our confidence level. So these guys over here, right? Those are directly connected into how we compute that z-score. And so it's super important to understand, as we'll soon see, that we get that confidence level, we take it, and we use it, theoretically connecting it to our sampling distribution idea. And we say, hey, I want to be confident that 80% of possible samples of this size corroborate or understand my level of surety, right? I want to take them into account when I do this calculation to create my margin of error. Or 90%, or 95%, or 99%. So what we're essentially doing is we are using this z-score and our idea of a sampling distribution to set a margin of error. So that margin of error requires our confidence level, and it requires us to be able to treat our theoretical sampling distribution, right, that I keep referring back to here, of possible sample sizes n equals 1004 of approval ratings for Joe Biden, for them all to take into account a sense of a normal curve, and for us to be like, well, I'm going to take into account 80% of those possible values, 90% of them, or 95 or 99% of them. Then the last bit to finish out that margin of error is p hat times 1 minus p hat over n. And I will go into more detail on this when we do specifically sampling distributions for proportions. But you might notice that once we've got this z-score, which by the way, I should say it's determined. I don't want to say that this z value here is the confidence level. It's determined by confidence level. This z value is actually called the critical value. Critical meaning it's incredibly important. Why is it critical? Well, it's kind of the thing that the confidence interval is named after, right? We call it a 95% confidence interval if we are finding a confidence interval that we are 99% confident in. And that's why it's a critical value, right? So this will denote how many possible versions of this one sample that we only got one version of we're taking into account of, with the understanding that we are assuming it's normally distributed. That is the number of samples that we would get, okay? So what have we done so far? We've found this equation for a confidence interval. We understand that a confidence interval is a sample statistic, a single sample statistic of a simple size, where we add and subtract a thing called a margin of error from it. And that gives us not one answer, but an interval of possible answers. And we call them plausible answers, answers that we would believe to a certain degree of certainty. Whether it's 80%, 90%, 95%, or 99% remains to be seen depending on the question. It could even be a totally different percent if they ask for one, but 95 is the most common. And we should hopefully begin to understand this idea of the margin of error is calculated using the idea of a sampling distribution, where we say, okay, I only took one sample of size 1004, for example, with this Joe Biden example that we see on slides 4 and 5. However, I could have taken that same sample size and used the same method and randomly done it a bunch of times, and there would be some level, right, of sampling error. Those values would vary in different ways from the true answer, right? And they would vary from one another a fair bit, which is totally fine. But what we do assume, and we'll see how we can do this in later lessons, we do assume that the distribution of all the possible samples in the multiverse of possible samples we could have gotten is normally distributed. Okay, so wait a minute. This is a brain blast moment. I want to sit with this for a moment. I want you to sit with me and take a breath, okay? I know you can't see me. But here, let me give you my face right now, okay? Here's my face. I'm just chilling. I'm not sad, I'm chilling, okay? We have figured out that we don't just use one number anymore from a statistic. We take that value, in this case a p hat, and we turn it into an interval. So now we have a series of numbers that we are ranging from, number 1 all the way to this other number, right? And that already excites me. You'll notice my eyes are starting to widen and a bit of a smile is coming to my face, okay? And here's the Doctor Strange multiverse version of things. not only am I taking this variety of values, and I'm saying I'm a certain percent confident, right? I am blank percent confident in my interval. I am saying that I am making that sense of confidence. In fact, I made the margin of error, the plus or minus that created that confidence, by looking at a theoretically normally distributed version of all the possible samples I could have taken of the same sample size following the same rules, right? It's like every multiverse version, but I accidentally picked a person with red hair that I interviewed versus one with brown hair, or a similar person who I randomly ended up having in this particular sample versus another particular sample. All possible worlds. And by all possible worlds, I mean samples that follow our rules, randomized, independent, normally distributed. We then take that and we use it to say, well, I want to pick an interval that accommodates or assumes the truth of 95, for example, percent of those possible realities actually containing the truth, the true population P parameter. And now my eyes are like this. Look at that creepy smile. I am blown away. Oh, my wife. No, it's a little, no, maybe it's more creepy. I am blown away, guys. This is the reality of what we are doing. Using a single sample, we are able to presume the normal distribution of sampling distributions, presume that we have done many, many realities of this one sample, and presume that a certain percentage of those intervals that we gathered from those theoretical samples we never even took would contain the truth in them. Not the sample truth, the parameter truth. All right. I have bloviated for long enough. Move on to slide 7 with me. This is just me talking a little bit more. Remember that the confidence interval, aka the CI in terms of how I'm talking, is always talking about parameter. I was just saying that a moment ago, wasn't I? We are using p hat to talk about p, for example. Or we are using, when we do means, x bar to talk about the actual true population mean. So confidence intervals are always about the parameter, not the sample. We use the sample, but they're not making theories about the sample. They're making theories about the true population proportion or population mean. Okay? Another thing to keep in mind, and this should make good sense, the higher your confidence level is, so as confidence level goes up, right, your confidence interval must essentially widen. Why? Well, because if you just want to be more and more certain in your values, you're going to want to hit more possible values, right? I'm more sure that there is candy within 1,000 feet of me than I am that there's candy within 50 feet of me. In fact, I'm pretty sure there's no candy within 50 feet of me, but we can all bemoan that right now. If you have candy near you, please send it to me. I just want candy so badly right now. I don't, actually. I'm exhausted. I'm tired. I want a cup of coffee. Now, with all of this in mind, what I'm saying here, and what should be noted, is that anytime you want to up your confidence level, it's inherently going to make that margin of error a bigger number, which is going to lead to a wider confidence interval. Why? Because you're going to need to hit more plausible values to be more sure that more of your conceivable multiverse confidence intervals that you might have gotten in all the many iterations in a normal curve of possible confidence intervals actually hits your population proportion. Similarly, if your confidence level goes down, your confidence interval can narrow. Okay, that should hit well. We're down to part 8, slide 8 here. Critical values, right? That's what I was talking about up here. The critical value, right? Z-score. Now, this is everything that we were talking about a moment ago. My critical value determines what percentage of the center of the theoretical sampling distribution of possible outcomes of my same sample size I am taking into account, and I am expecting to actually hit the real answer. So here's the way to think about it. Let's say I have a sample. Let's say I took a sample, like I said before, of 1,004 people for an approval rating. Okay, that's my N sample size. When I'm picking a critical value Z, okay, Let's say I want to be 95% confident. That's the level I want, confidence level. Well, that means I want a z-value that represents that. Now, let me show you how we're going to get that. First, we assume a sampling distribution. All the circles represent theoretical samples of size n equals 1004 samples. Okay, so these are all theoretical samples, and they are normally distributed. Okay, I want to accommodate for 95% of them actually capturing the true answer. Because one thing I want you to have, and you should have this in your notes, okay, your confidence interval does not necessarily capture the true population parameter P. Okay? You don't necessarily have it. So when you do the interval, if someone says, what are the odds, is it possible for the true population P to be something outside the interval? Of course it is. It's possible. It's not plausible. It's not probable, I should say. I'd say it's improbable, but it is possible. Okay? Excuse me. So that's the first thing to note, right? A 95% confidence interval says that 95% of possible intervals I could have gotten in the multiverse of possible intervals is going to capture the true answer. That means 5% of them won't. So it's totally possible that we don't capture it, right? But this is what confidence truly means, what it represents. Okay. Here's the thing to keep in mind. Looking at this sampling distribution, I'm going to make another one down here, okay? It's normally distributed. Within one standard deviation either side of the true parameter, right? Of the center. This is now the mean proportion. So we have that. The proportion mean, the mean of proportions. The mean of your p-hats in our sampling distribution. Within one of either side holds 68% of our data. Within two of either side, that hits 95% of our data. And then 99 and so on and so forth. Now, what I want you to notice is that not 95% is just like the 95% from our confidence interval. My goal is to accommodate for 95% of possible universe answers for confidence intervals, having 95% of those possible intervals capture the true population proportion. So I want to find this z-score. I want to find the z-score that sits up here at the upper end if I'm capturing the middle 95%. Now what you'll notice is if you're capturing the middle 95%, these two slivers on either end are of 2.5% each. Right, 95% in the middle, 2.5% on either side. So to find my critical value, by the way, is right here. It is the upper end of your middle data gathered interval, right? So the upper end of the middle 95% is the z-score I want. So what I do is the following. Here's how I know how I'm finding the answer. I take my total, 100%. I subtract my confidence level I'm looking for from that, 95. I get 5. Now there's an upper and lower tail, like we mentioned. So I will divide 5 by 2 and get that 2.5. Now I don't want to find where the 2.5th percentile is. That's the lower end. I want the upper end z-score because that will accommodate all of that middle area. So what I will do is I will take that value, right? And I will do the thing that all great people will do, which is I will just subtract that from the total 100%, again, 2.5. And lo and behold, and this should make sense, we actually want to find the z-score for the 95.7th percentile of the sampling distribution, right? That's the z-score we want. So for a 95% confidence interval, you want the percentile for the 97.5 percentile. So this is what you'll do anytime you want to find the critical value for a particular confidence level. You'll subtract, right, the confidence level from 100. You'll divide your answer by 2. Then you'll subtract that new answer from 100, okay? Then you'll do inv norm because you want to find the area under the curve, right? And use that area under the curve to find a z-score. So inv norm, the area under the curve, is the decimal version of 97.5%, which is 0.975. Your mean, because we want a z-score, is 0, and our standard deviation is 1. You can throw this in your calculator, and lo and behold, you should yield an answer of about 1.96. And that will be your critical value for a 95% confidence interval, okay? On slide 9, I go through the components again of a confidence interval. The statistic, the sample statistic, in this case p hat, plus or minus, okay, critical value, that's z, times our margin of error, the square root of p hat times 1 minus p hat over n. You'll notice, again for my astute watchers, that this second part of the margin of error is actually just the same thing, and this is kind of dope. It's actually just the same thing as the standard deviation for a sampling distribution for proportions, right? So it's literally just we're taking the standard deviation and we're saying, I want to go z standard deviations in my sampling distribution outward, right? Of possible sampling distribution answers, I want to take into account all those theoretical realities, like Dr. Strange might. I'm not even a big Marvel fan, honestly, guys, but this is a perfect way to express it. Okay. You don't need to use that in your answer, but just be aware of it, that that's what's there. But remember that this whole chunk here is called the margin of error. Margin of error. I'm supposed to practice my Chinese today. Ni hao ma. Okay, so that's what we're saying on slide 9. Now, just tucking back in, what that means for my Joe Biden confidence interval, right, is that, for example, if I wanted to solve this out, I would go and I would put my p hat in, I would do plus or minus, and my z critical value would be 1.96. And then I would do same p hat times 1 minus p hat over n. Okay? So, if you are like, oh, I want to make sure I can still do this, calculating the critical value for a variety of things, I want you to note that there are slides, visuals on slide 10, 11, and 12, just walking you through all of the different critical value calculations you might see. And then if you go to slide 13, you can test and see how I solve for a critical value of 80% confidence level, okay? You'll walk through the same step-by-step process that I just did here for the 95% confidence level, but this is for 80%, and you'll get a critical value of about 1.282, which is correct, okay? With all that in mind, really quickly, I want to solve for a confidence level for proportion, confidence interval, I should say, for proportion, before I finish out this slideshow and talk a little bit about what confidence level truly means. So let's say I took a sample of, I think what I did in class was something like, let's say I found out of a sample of n size 52, that there were 35 of you that, I don't know, love the color green. Let's say you love the color green. Why not? Let's love the color green today. So this is our value x of people that love the color green. Well, what I would do is I would then begin to solve, and I would say, what about for a 95% confidence interval? Okay, that's my confidence level for my interval. Find me a confidence interval. Well, what I would do is fairly simple. I would find p hat. How do I find p hat? I would do 35 divided by 52. And that would yield me a p hat of about 0.67. From there, what I must do, if I am to find answers and roll well through my solutions, is I will use my equation. P hat, 0.67, plus or minus 1.96, because I want a 95% confidence level, times the square root of 0.67, times 1 minus 0.67, over sample size, 52. And you would solve that, and that will give you your margin of error. Now I'm going to calculate it real quickly. Let's see how fast I can do this. We do 0.67, and we do times 0.33. We then divide by 52. Remember your order of operations. Don't make tiny mistakes, okay? Then we square root that. And hopefully you're doing this alongside me. Then we multiply that value by 1.96. And again, what we're doing here is we are multiplying the standard deviation value for a sampling distribution of samples of this size for proportions, and multiplying it by the critical value of how many z-scores away we want to be. I get about 0.13 as my margin of error. So it will be 0.67 plus or minus that. So my confidence interval will be 0.67 0.8-ish on the high end, actually, which should be, I did this silly, 0.8 on the high end, 80. And then on the low end, we're looking at 0.54. And that would be my confidence interval. And so here is the thing that shows up in future slides, specifically when we get to slide 14, okay? If I said, what does this confidence interval mean? Here's what I would say. We are 95% confident that the true proportion of AP Stats student, and you have to give context, so whatever it is, AP Stats students who love green. Y'all, my handwriting is getting hideous here. Let's fix that. How about we clean up the act, Mr. Mays? Who love green is between 0.54 and 0.80. Okay. So if they say interpret the confidence interval, right? Interpret. You would say we are 95% confident that the true proportion, you'll write out proportion, of AP Stats students who love green is between 0.54 and 0.80. But as it says on slide 14, and I want you to just go to slide 14. I'm going to read it out loud. I'm not going to write it out, but I'm going to read it out loud because it must be read. Okay? If they say, what does 95% confidence level mean? Or they ask you to interpret the confidence level. Here's what it means. And I've already said this a few times, but here's what you will say. If we take many random samples of the same size, n equals, in this case, 52, right? Of sample size 52. And constructed 95% confidence intervals from each of those samples. About 95% of the intervals, not of the samples, but of the intervals that we capture from each sample would capture the true population parameter of, and I would have to clarify what it is, AP Stats students who love the color green. So you should, from this video already, have an understanding of how to interpret confidence interval and confidence level. Right? Definition was in the slides on slide 14. Right? Super important. Okay, have that in your bucket. That's super important. You will notice for slide 15, this is pretty close to what a 95% confidence interval looks like. You will notice that every single one of these lines, so every one of these lines represents a confidence interval with the center dot representing the sample proportion. Right? And then they extend equal sides on either side. You'll notice that if the dotted line going down the middle is the true population parameter, what you'll notice is that all of these confidence intervals have captured the population parameter except for one, right? And in total, there are what? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 5. That means 1 out of 25. This is on slide 15, by the way. 1 out of 25 confidence intervals failed here. It did not capture the true population proportion, right? Now, 1 out of 25, that's the same as about 4%, which means that 96% of confidence intervals captured the true population proportion. Now, that is about a 95% confidence interval. Right? If you were to ask me, which confidence interval is it? Is it a 90%, a 95%, or a 99%? I would say that on slide 15, we are looking at a 95% confidence interval. And I determined that by calculating the percentage of confidence intervals that were pictured there that actually captured the true parameter given. Slide 16 allows you to do this again. Okay? And it says, give me the point estimate and the margin of error would be the distance from the middle to either side. That's just more information. Slide 17 further goes into point estimate, margins of error, and things of that nature for each one of those lines, and hopefully that clarifies things. Slide 18, we go through once more this definition that I've already mapped out for you of we are 95% confident that blah, 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 blah. Do know how to interpret confidence level and interval and know the difference between the two. Slide 19, you will see 2 practice problems. You should complete these. If you have questions about solving them or have struggles with any of them, reach out to me on Remind and I can show you some solutions for them, or come find me after school and I'll go through them. But I would drill through those. Okay? Slide 20, you will note it says, which of the following of these are both sample statistics, point estimates? You'll notice only answer C is correct because answer C gives us p hat and x bar, both of which are sample statistics, not parameters. And the final question on slide 21 says, what does the parameter describe? The parameter, of course, describes A, the population, not the sample. The sample statistic is for the sample. And I lied to you because actually slide 23 has our last question. It says true or false? No, that's not true. Slide 24 has a question too. Don't listen to me. Let's do these two together though. Slide 23 says 95% of the population distribution is contained in the confidence interval. Is this true or false? The answer is that is false. The confidence interval is talking about a parameter, not about samples. We are using samples to determine things about a parameter. On the other hand, slide 24 says we calculate our confidence intervals using a method that gives correct results 95% of the time, and that's true if we are using a 95% confidence interval. Again, correct and true in the sense that if we were to theoretically take many samples, all of the same size as the sample we did take, and collect confidence intervals to a certain level, let's say 95% for each of them, we would assume, and we would be correct in assuming, we would expect that about 95% of those intervals contain the true population proportion. All right, you've done a lot with me today. We've talked about confidence level and confidence intervals. We've learned how to calculate one for proportions a little bit. We've looked at some examples. We've talked about what a margin of error is and how it's the plus or minus that we apply to our proportion or our sample mean when we get to that to determine our confidence interval. We've talked about the way that a confidence interval is basically taking a sample statistic and we are expanding it using the idea of sampling distributions to talk about basically the metaverse of all the conceivable possible realities where we took varying samples of the same size using the same method, but where there's sampling error involved, right? We've then gone through and learned how to determine how to get our critical value that allows for that, depending on the confidence level. We've done some beautiful drawings of how we have blown our own minds, and I will end with this idea for you, okay? Confidence intervals are the beginning of high-level inference. They are the first time where you are not given a pie-in-the-sky truth. You are instead asked to evaluate what truth might look like. We live in a world where truth is constantly evolving. Every second, the rational, true population proportion is shifting. People are being born and dying. Data is coming into existence and devolving from existence. I want you to realize we have entered, and you have entered, the first part of your journey of determining the variability of truth. Because truth is not an answer, it's an interval, okay? And it's not a certainty. It is something that we are a certain level of confident in. And thank you for taking this journey through the many realities and determining that in 95% of those intervals, we captured the truth of life, the universe, and everything. And I couldn't think of a better batch of students to take that adventure with. I appreciate you, I adore you, and I am so thankful to teach you. Study up, know your things. This is Mr. Mays signing off.